I forget. So last time we were discussing the shell method to find volumes of solids of revolution, and we also concluded the previous section on cross sections and disc washer method. So one of the main differences between the disc washer method and the shell method is when we have our regions to be rotated about a horizontal axis, we use functions of x with the corresponding axis when it comes to the disc and washer method. However, everything reverses when it comes to the shell method. And in this case, well, we got to do one example in which we had the axis of revolution below the region of integration. And well, when it comes to that, well, that gives us this R right here, which is, in this case, it's given by a vertical distance y minus the position of the axis of rotation, in this case the horizontal axis. So now we're going to have a region, the same region actually, but rotated about an axis in which in this case is at the top of the region of rotation. So let me redraw the picture so you can see what is exactly what we are expecting to see. So in a way it's going to be a solid like that. All right, well, in this case, now what do we have? So let's write down the formula for the shell method so we can describe and how we're going to set up. So volume equals 2 pi integral c to d r of y, that's the radius, and then that's the height, and with respect to y. All right, so from here, well, so r of y will be that distance from the axis of rotation, which in this case in this case it's the top minus bottom. So in this case the top will be the axis of rotation, which happens to be 4, and then in this case minus y, which is the number of units or the radius of the region. Again, in the terms of the example about the lollipop we discussed a few times last time, well, this y is the number of flavors the lollipop has, right? So, and then h of y will be described in this case in terms of functions of y as the rightmost minus leftmost. In this case, that's the shape of the region or the shape of the candy, if you will. So setting the integral right here, we're going to get 2 pi integral from c to d. For the limits of integration, I believe I was supposed to get, well, for the limits of integration, so let me get back to that part from the previous example. So that's x equals 0 and x equals 1. So that's the order pair 0, 0, and well, in this case it's 1, 1. So in this case the limits of integration are going to be 0 and 1, 0 and 1, regardless of the direction of the function that we take. So in this case 0 to 1, 0 to 1 for the previous case as well. So the radius, which is going to be the axis minus y, which is 4 minus y, times, in this case, the rightmost minus leftmost, but notice in this case, the rightmost, it's going to be the curve defined by y equals x squared, but in this case, we're using functions of y, not functions of x, so that's going to be x equals to root of y, and in this case, the line y equals to x is the same as x equals to y in terms of y. All right, so that's x equals to y. That'll be then root of y, which is the rightmost, minus leftmost, which is simply y. And that with respect to y. Question?
Yeah, on the first example, why did you do y minus the line? I feel like you did y minus line, and the second one you did line minus y.
Yes, so in this case, for example, when we describe the radius, the r of y, so we look at the region, and in a way we do the top minus bottom, and in this case the top is whatever radius is, which is in the direction of y, minus the position of, or the location of the axis of rotation. And over here is the reverse. Here the highest point would be the axis of rotation, which is 4, minus the radius y. You're welcome. A pleasure. So number 5, so it's the same region in this case, but in this case, well, what are they asking us to set up? So they're asking us to set up, do not evaluate the integrals that find the volume of a solid when the region is bounded, y equals x squared and y equals x, but in this case about the lines, so two different regions again, x equals to 7 and x equals to -4. So what are we going to have in this case? We're going to have vertical axis of rotation, which in this case, well, that's going to ask to use functions of y. So let me point that out over here. So rotations about vertical axis, that means need functions of x. Okay, as opposed to, did I know that in the previous example? Okay, so in this case I need to point that out as well. Rotations about horizontal axis need functions of y. Okay, so let's have a look. Let's sketch the region, of course. So what are we going to have? So number 1, the Cartesian plane, and let's draw the parabola and the diagonal line. And in one case we want to rotate this about the vertical line, x equals to 7. So let's pretend that x equals to 7 is somewhere here. Alright, and we're going to do the rotation in this direction. So we are going to obtain a solid, like a horizontal solid, right? It's a horizontal rotation about vertical axis. Okay, so, well, in this case, this is going to be projected pretty much this way, right? And I'm trying to make it look like a solid. That's our rotation. Is the picture clear with what we're trying to get? Does it make sense? So from here, let's see, what do we have? Number 1, since we are going to use functions of x, we are going to describe a top, which is y equals to x, and the bottom, which is y equals to x squared. In this case, we don't solve the equations like in the previous problem, because we're looking for functions of x and we're given functions of x in this case. So let's see what we're going to get. So number 1, we also, okay, let's write down the formula, and then from the formula we are going to obtain or visualize better how we set up the integral from a to b, r of x in this case, and h of y dy. So number 1, the radius right here, which is the distance between the axis of rotation to the outermost point in the rotation. In this case, the outermost point is rather given by x because it's a horizontal distance. So the solid spreads in a horizontal direction. But number 1, what's the, well, this is x equals to 7. Which one would be, in this case, the outermost? We go rightmost minus leftmost. In this case, the rightmost is the axis of rotation, which is 7 minus, well, in this case, is x, just x. Because x is the radius of that solid. In this case, when we rotate it horizontally, we are creating a horizontal radius that we call x. Or again, in terms of the candy, that's 7, which is the location of the stick of the candy, minus the number of flavors, if you will. So this part will be v equals to pi integral from 0 to 1. They're the same limits of integration. There is the same region that we have been working on. That's 7 minus x times the height. In this case, well, the height, I guess it's the easiest one to describe, because that's the top minus bottom that we have been doing for a while now. And in this case, the top happens to be the diagonal line, which is x minus x squared, and that with respect x. All right. And for the last example, which is another setup but do not evaluate, we're going to have the same region. The line, the diagonal line, and the parabola. And in this case, we want to rotate this about the axis x, the vertical axis, x equals to -4. So I'm going to go over here. 1, 2, 3, 4. We're going to have the axis of rotation here. We're going to rotate the region. Yes. Which one? Oh, yes, yes, yes. I don't know what happened here. Yes, that's true. That's h of x and the x, right? Whoops. Thank you. And so when we rotate this, we should get the following. Again, let's try and make this look like a solid. I know it's not easy to make this look solid. Hopefully we get the picture in this case. Well, so in this case, let's describe the r of x and then the h of x. So let's write down the formula. V equals to pi integral from a to b, r of x, h of x, dx. Okay? So, let me use the screen. So from the axis of rotation, in this case, we are going to go to the outermost point, which in this case is x minus the position of the axis of rotation, which in this case happens to be x equals -4, which is x plus 4, right? And the top minus bottom, I think that's the one that it's easy to describe in the same way that we did it with the previous part. So volume equals to pi integral a to b, r of x, which is again x minus -4, times top minus bottom, that's x minus x squared with respect to x. And well, all we have to do here is clean up the negative here, clean up the negatives, and write this as v equals to pi. Oh, I forgot the limits of integration, 0 to 1, x plus 4, x minus x squared with respect to x. And that'll be the setup of the integral. And again, on the exam, most likely you will be seeing a problem like this, in which you will be asked to set it up on. And that's because this would give rise to an integral that may take a good minute to compute. I mean, like 20 minutes, maybe 25 minutes. And on top of that, well, you will still be tested on other topics, so time is going to be valuable, unless you get like a more simpler region of integration in this case. Well, so In that case, you might be asked to compute the integral and provide its value. But in other cases, you may be asked to just set up the problem. All right. So let's see the next topic. So that ends solids of revolution. The next topic is section 6.5 on average value of a function. All right. So the average value of a function, you can think of it as the mean value theorem for integrals. Well, number one, let's recall what the mean value theorem from Calculus 1 is. Essentially, the mean value theorem, I typically call this where the algebra meets the calculus. So I'll show you the picture and I'll explain what do I mean by that. That's the big. So the idea is that we have some function f of x, all right, whatever that is, it doesn't matter. And well, so for f of x, for the mean value theorem from Calculus 1, mean value theorem, MVT for short, well, the idea is that the slope, the mean value theorem, we're looking for a value in between a and b such that the slope of the secant equals the slope of the tangent. That's the idea with the mean value theorem. That is, in other words, okay, so we have this secant line right here. Recall that a secant line, it's a line that includes 2 points or crosses at 2 points on a function f of x. So it should look like this. All right, so that's the secant. And well, of course, between A and B, how many tangent lines can we trace in between A and B? Infinitely many, pretty much, right? Many tangent lines. But we're looking for a very specific tangent line, only one. A tangent line that has the same slope as the secant in this case, and I'm estimating somewhere here, right? And well, what's the characteristic of a tangent line? Isn't that a line that only crosses at 1 point on a function f of x, right? Well, so yes, in this case, this is the value of c that we're looking for. That value of c where the slope of the secant is equal to the slope of the tangent. Okay, well, let's put this in context, well, in formula context rather. Well, so the slope of the secant line, well, to get the slope of the secant line, we have 2 points. All we do is the rise over run between the 2 points, right? y2 minus y1 over x2 minus x1. So that's y2 minus y1 over x2 minus x1. So let's call this p1, which is the x1 y1, and let's call this p2, which is x2 p2. Okay, and that should be equal to, well, the slope of a tangent line. Well, how do we find the slope of the tangent line? Do we still use the rise over run formula? How do we do that then? We're using the derivative, right? So what we do is find the derivative of the function, and in this case evaluate it, not just any value of x, rather this value of c. This value of c will have the slope of the tangent that will be the same as the slope of the secant line. So that was the mean value theorem back in Calc 1. Did that ring a bell from Calc 1? So let's have a look at analogous idea for integrals. So again, the average value of a function, for it's basically the mean value theorem for integrals. Well, in this case, we we found the slope of a secant using algebra, we found the slope of a tangent using calculus. So that's why I call this where algebra meets calculus in the same problem. We're going to do something similar with the integrals. However, we use the integrals to find areas, not slopes, as opposed to the derivative. And in this case, well, if we consider some region again, if we consider some f of x again between a and b, all right, let me change this so that it makes more sense, and b, and well, in this case, what are we going to have? When we evaluate the function at a, this y value will be f of a. If we evaluate our function at the value of b, well, this will be f of b. All right? And well, the integral in this case, again, that's going to give us the area under the curve. All right? But well, how do we find the area of that we're looking function, or rather that we're looking shape? Well, using the integral. So we cannot measure the dimensions of this curvy edge right here, so we can find the area the same way we did it with rectangles. All we do, grab a ruler, measure the dimensions, multiply length times width. Well, that's easy to find. But in this case, well, we're going to find a value of c, right in the middle somewhere, f of c and c, such that the area under the curve is the same as the area under the rectangle here. All right. So in the mean value theorem for derivatives, we found the value of c for which the slope of the secant without calculus is equal to the slope of the tangent, in this case with calculus. So we're going to find the value of c for which the area under the curve with calculus is equal to the area under the rectangle without calculus. Well, to have a better visual of this picture right here, suppose this weird looking region is what's it called, peanut butter. All right, suppose this is peanut butter, and what am I going to do? I'm going to get a knife here, and I'm going to change the shape of this region. So what am I going to do? I'm going to push this a little down, I'm going to push this a little up, and I'm going to push this a little down until I get a perfectly rectangular shape right here with this peanut butter. So what's going to happen? Well, when I push down, push up, and push down, I'm going to get like an average, right? So once we do the process, well, those two areas have to be the same. And well, so this is what actually the f average value is. So when we calculate that f value, or rather that c value, that's going to be the value of y, that c value in between f of a and f of b, for which the two areas will be the same. Okay, so let's do an example so we can illustrate this. So the formula is very simple. It's nothing other than finding the area under the curve, but in this case we divide by the length of the interval, so that's basically the average, right? Question. The f of c? This one? Oh, that's the value that we will find in that actually will be the final answer. So well, once let's look at the example, so we can relate that c with oh yeah, I see, yes. So let's call this number average, f average. Yeah, I see what you mean. Let's call it f average, right? So let's see. Let's look at one example, a very brief example. So find the average value of the function f of x equals x squared plus 1 on the interval -1 to 2. So number one, how about we graph the function? Okay, so the graph of f of x squared of f of x equals x squared plus 1 is that of a parabola shifted 1 unit up. That means, that's going to be 0, 1, -1, 2. Okay, it's only -1. We don't want the whole graph, only from -1 to, okay, that's 2, and that's going to be 5. All right, so that's the graph of the parabola within the limit a and b, which are -1 to 2 respectively. So let's shade the area under the curve, and that's the area that we want to find. So we are going to find that value of y, that f average, that will turn a rectangle equal to the area of that we're finding in here. So let's see, let's do the calculation. F average that's 1 over b minus a, integral from a to b, f of x with respect to x. Well, b, which is in this case 2, minus a, which is -1. Be careful with the signs in here. That's the integral from -1 to 2, x squared plus 1 with respect to x. And well, this integral is going to be very simple to integrate because it will require only the general power rule, but 2 minus -1, that's going to give us a third, and that's the integral of x squared, that's x cubed over 3, and the integral of 1 is x, and this evaluated from -1 to 2. Well, so the usual 1/3, that's 2 cubed over 3 plus 2 minus -1, careful with signs here, cubed over 3 plus -1. So let's do the arithmetics here, or well, actually I'm just gonna go give you the answer to this bracket. So I'm gonna get 1/3 here, and when we simplify all this quantity inside of the brackets, that should give us a 6, and 6 over 3, that's 2. All right, well, what is this number right here? So this is what we're gonna get, 2, which is f average. All right, that's the, so I'm going to create another Cartesian plane here, and I'm going to graph that f average, which is, well, number 1, 2, 3, 4, and this will be 2 from -1 and 1, 2. So what's the area of this rectangle? Isn't it, well, 1, 2, 3 units, 3 times 2, which is 6? Well, if we find the area, well, without the 1/3, which makes the average, isn't that the same as 6 right here? So again, what did we find? That f average, it's the value of y, the height of the rectangle, that would give us the same area under the curve, under the we're looking curve, to be equal to that area of the rectangle. Right? If you compute the integral separately without the 1 over b minus a, so that's going to be this area right here. So that's why I did it on purpose here to get, and let me label this area under the curve. Area under f of x, and that times 1/3, that's the average value. And that's the picture. That's the picture with one example. And again, this section is very brief. It's only one example, so you might see only like 1 or 2 examples on the homework. There's really not that much other than seeing the definition and really comparing the idea with the mean value theorem for derivatives, which discussed in Calc 1. All right, so for the next topic, so we're going to move on to a new chapter. Where is it? Right here. So, and we're going to get in depth into the methods of integration. So, in Calc 1, you finish the Calculus 1 course by getting into the integration, basic integration, the general power rules, some basic integration formulas like the exponential, the trigonometric ones, maybe some integrals that gave rise to inverse trigonometric function. But I mean, those are really not the method, those are just formulas. Here we will discuss the methods of integration. Maybe the one that you did in Calc 1 is the U substitution method. That's the only one that you might have covered. So we move on, we will take it from there and discuss the integration by parts method. But well, I could just give you the formula and solve a few problems, but it's important to consider where is this formula coming from. And well, you can think of the integration by parts in a way as the product rule of integration, but be careful here because you know the derivative of a product, which is the derivative of the first factor times the second plus the derivative of the second factor times the first function, the first factor, it's not the same with the integral, so it's a different setup. However, this actually comes from the derivative of the product. So okay, so consider the product of a function u times v. All right, if we take the derivative with respect x, what are we going to get? Well, that's u prime v plus v prime u. Right? Okay, so from here let's find the differential. So to find the differential, well, actually let me change the notation here so this makes more sense. ddx uv of the product u and v. Instead of writing u prime, I'm going to change this to du dx times v plus dv dx times u. And well, we're going to find the differential. To find the differential, we multiply both sides by dx and see what's going to happen. It's going to cancel here, and this will cancel these two as well, leaving us with the following. That's going to leave us with d uv equals v du plus u dv. Well, so the idea here is to go back and integrate this, so because that's what integration by parts is doing, the product rule in a way, but in the reverse order. That's why I mentioned it's in a way the product rule for integrals, but we don't perform a product of integrals. It's the product rule of differentiation, but backwards. So if we integrate this, if we integrate both sides, we want to solve for the integral of u dv, which is cancel, that's going to be uv minus this term right here, the integral of v du, which is the formula that we have over here. All right, so again, that's the formula, but most importantly, where is this formula coming from? It's actually working with the product rule of differentiation, but backwards. All right, so let's see. When it comes to working with integration by parts, we need to do a setup that includes a u and a dv. The u is a function that will be differentiated, and the dv part of the setup will be the function that will be integrated. Well, it's important to understand how do we do the setup, because if we do these setups in the backwards way, we may end up making the problem even more complicated than it actually is, and in fact we would be ending up in some sort of infinite loop, making the problem infinite without a solution. So so there's a few guidelines here. So and while we go through this method when straight U substitution doesn't work for the integrand that we have, all right? And usually we take the dv, the most complicated portion of the integrand, and U, the easiest one to differentiate. Well, that's a little, I find that a little vague, because, well, what do we mean by easy? What do we mean by hard? Well, in this case, there's an alternative to this, which is using this acronym called LIATE. What does that stand for? Well, this LIATE thing is going to help us choose the U first. Once we get the U, the dv comes next. All right. So what do we mean? So the L in the LIATE is for logarithmic functions. So we will observe our integral. Do we have any logarithmic functions? And not just ln, but logarithmic functions of your favorite base. Do we have, the next stands for I stands for inverse trigonometric function. Does our integral contain arctan, arcsine, arccosine? Well, that's going to be our U. The A stands for algebraic functions. Well, by algebraic functions we mean polynomials or powers of x, and in this case not just powers of x that are integers, but also radicals, which are really powers that are rational. And one I didn't type over here, we could have negative powers, x to the -2, x to the -7, so we can have those as well. The next letter in the LIATE acronym, it's T for trigonometric functions. Well, we know the 6 trigonometric functions, there's not much to say about it. And last in the hierarchy here is the E on the LIATE acronym, which stands for exponential functions. And well, in this case, exponential functions, e to the x, 2 to the x, whatever base we have. It's not limited to just e to the x. Any base works. Well, so I guess the best is seeing this in action. How about we look at one example? So we have the integral of x e to the 3x, and well, so number one, let's choose the two parts right here. Number one, we need a U and we need a dv. So let's use the LIATE acronym to help us get the U first. Okay, so let's write it down. Okay, let's start with the L. L stands for logarithmic function. Do we have any logarithmic functions in our integrand? Yes? No? No. Okay, I. Do we have inverse trigonometric functions? No. Do we have, what's A? Algebraic function. Do we have any algebraic functions? In this case is x. Okay, well, that being said, x is the U part. The remaining part of the integrand, including the dx, will be the dv part. So what are we going to do? The U differentiated, the dv integrated. So what's the derivative of x in this case? Well, that's du. That's equals to dx. And well, v will be the integral of this. That's the integral of the exponential, which is e to the 3x times 1/3. And we have the 4 parts that we need for our setup here, so we can evaluate this integral by parts. All right, so let's see. So let's, by the formula, which I'm going to write it here, that's the integral of u dv. That's u times v minus the integral of v du. Well, so this is what we do. We're going to multiply u times v, which in this case is x times 1/3 e to the 3x, minus the integral of v, which is 1/3 e to the 3x du. Okay, let's label this just so you can see everything. So that's u times v minus the integral of v du, which by the way, this should have been dx. Alright? Well, there's not that much to do over here other than writing this in order. So I'm going to write this 1/3 in front. And I'm going to take this 1/3 out of the integral. And all we need is to compute this integral of e to the 3x with respect to x, which we already did, right? We did it when we were setting up the problem. So that's 1/3 x e to the 3x minus 1/3 times the integral of this e to the 3x, which is itself e to the 3x plus c times another factor of 1/3. That comes from the integration of this exponential. And well, let's just multiply 1/3 x e to the 3x minus 1/9 e to the 3x plus c. And of course, we can verify this by differentiation. If you take the derivative of this function, you should obtain this x e to the 3x back. I mean, because that's what we should expect to obtain, because integrate someone's derivative, you get the original function, take the derivative of that function you obtained, that you recovered, you should get back to the original function that we were integrating in here. Alright, so let's do another example. Let's see. Number 1, before doing the setup for this integral, if we see fractions, I mean denominators, it's important to write everything as a product, not as quotient. In this case, we will rewrite this as x to the negative 2 ln of x with respect to x. Now, number 1, let's go with the LIATE acronym, and let's set up the u and the dv parts. U equals dv equals number 1, L, which stands for logarithmic function. Do we have any logarithmic functions on the integrand this time? We do, so that's the u, ln of x. dv will be the remaining part of the integral, that's x to the negative 2 with respect to x. What are we going to do from here? Take the derivative of the u part, take the integral of the dv part. This looks like a y, let me write it down again. And the derivative of ln x, which is, well, du equals 1 over x dx. And then integrate the second part, that's v. Well, the integral of x to the negative 2, add 1 to the exponent, that's negative 2 plus 1, is that negative 1 over negative 1. And well, let's clean up the messy negative signs by having the negative in front, and x to the negative 1, let's write it as 1 over x. So we have all the 4 parts that we need to set up our problem here. So let's go back. That is, so again, let me write down the formula. So the integral of u dv, it's u times v minus the integral of v du. So u times v, that's going to be ln of x times negative 1 over x, alright, and minus the integral of v, which is negative 1 over x, times du, which is another factor of 1 over x dx. So first of all, before attempting to compute this integral, let's clean up the parentheses, let's clean up the negative exponents and the like, alright? So number 1, I'm going to write this negative 1 over x in front of the ln x to make it look like negative 1 over x times ln x. And this one is going to be negative times a negative, which will become a positive. And 1 over x times itself will be 1 over x squared with respect to x. And then from here, well, we cannot integrate these powers while they are in the denominator, so let's move it to the numerator. Negative 1 over x ln x plus the integral of x to the negative 2 with respect to x. And well, we're ready to integrate this function. Negative 1 over x ln x, add 1 to the exponent, that's x to the negative 1 over negative 1 and plus c. But in the end, let's just fix all these negatives. So plus a negative quantity, that means to subtract, and that's 1 over x and plus c. All right.